Welcome to another exciting adventure in ECE 442-542. This is exam number 2 review, and I swear I did not take those study buddy pills, although it might appear that way in the remaining time that we have together. Exam 2 process we've already talked about earlier, and I won't spend time with that. You can read that at your leisure. Exam number 2, the review, is basically the contents are just homeworks 3 and homework 4. Homework 3, what you need to be thinking of when you hear homework 3 is region of convergence and inverse Z transform. You need to be able to do those two main things. And when you hear homework number 4, it's discrete equivalence. So now what I want to try to do is provide some ways of thinking about this in terms of these two concepts or these two categories. It's really sort of 3 different concepts. We'll talk about region of convergence, inverse, and how that's related to inverse Z transforms, and then discrete equivalence. And we obviously have a lot of different conditions on those two sets of topics. Now, in terms of region of convergence, there's really only 3 types. And any of these region of convergences, no matter which one, and hopefully this will be clear when I sketch those, and what I'm meaning by saying it's connected, we cannot have 2 pieces of the region of convergence that are disconnected. 3 types of region of convergence. I'm going to call 3 different things. I'm going to say we have an inner region of convergence that looks like that. We have an outer These are the 3 types. We have an inner, we have an outer, and we have an annular. And the annular then is essentially an intersection of the previous 2 in some manner. Meaning now we have the region of convergence that is a donut shape. Those are our 3 different types. And now all you really need to know is what happens relative to those 3 different types of regions of convergence. To understand that, we can go back to our definition of the Z transform. The Z transform in general is this infinite sum from minus infinity to infinity, let's say of x of n, z to the minus n, which we could come up from the negative infinity side and then say that we have x of minus 2 times z to the minus 2, or now we have z squared, scaling x at time index n equal minus 2, plus x of minus 1, z to the minus 1, or z to the 1, plus x of 0, z to the 0, which we don't really even have to write, that's 1, x of 1, z to the minus 1, plus x of 2, z to the minus 2, and on out. That's our definition of the Z transform. And what we know is that these region of convergences gives us values of Z where this expression for capital X of Z has to be well behaved, or it converges, or it's bounded. So I'm going to say X of Z must converge, or give us a number, a bounded value. Capital X of Z must converge for all values of z in the region of convergence. Meaning, we only have 3 different types of regions of convergence. We pick a z in one of those and we plug it into this definition, and that will actually tell us something about the time indices that have to be non-zero or the time indices that have to be 0. Let's see what that means. So let's say that we now have what I was calling an inner region of convergence. That's this picture, the first one. Suppose now that the values of z inside this shaded region allow the expression, the definition of capital X of z to converge or to be bounded. And what's a convenient value for z in an inner region of convergence? An easy one might be the origin, z equals 0. That means if we go back here to this definition and plug in z equal to 0, whoa, that's not going to be well behaved if x of 1 is non-zero. If x of 2 is non-zero, it's not well behaved because we're dividing by 0. That's going to go unbounded. That inner region of convergence structure says that all of these non-negative indices or positive indexed values of x have to be 0. Let me say with an inner region of convergence, and where are your poles? Did I say that yet? The poles cannot live in your region of convergence. Your poles have to be out here, don't they? They have to be outside of the region of convergence. So with an inner region of convergence, which says that the poles, and here's the terminology I'm going to use, the poles lie exterior to the region of convergence. They're outside of the region of convergence. But what did we say examining this transform? This told us that we can only have non-zero values of our time index for what values of n? N negative, right? Those are okay to be valued. The others have to vanish. N's greater than or equal to 0, those have to vanish when we have an inner region of convergence. So if we have an inner region of convergence, our time index is going to be negative values of n. So we have a one-sided sequence, and in fact, that's a left-sided one-sided sequence. We found this by, if we wanted to, we could examine x of 1, z to the minus 1, x of 2, z to the minus 2, etc. And that said that x of n must equal 0 for n greater than or equal to, well, at least greater than 0. Okay? That's why we can only have negative indices when we have an inner region of convergence. Is that okay? We have an inner region of convergence. If your region of convergence looks like this, it's inner, then you know your n's are indexed for negative values. Positive value n's can't exist, or they're equal to 0, your values of x at those points in time. What about outer? That's one region of convergence. If we do an outer, boy, that's looks like I'm on that study buddy. outer region of convergence. Here I'm going to say that this says that the poles lie interior to the region of convergence. By that I'm saying that the poles now are in here. They're interior to the unshaded region with an outer region of convergence. Now, if we go back to this expression, what's a convenient value for a z-value inside the region of convergence that the transform has to converge for? Now think way over here, right? A big value of z, an infinite value of z. That's inside the region of convergence, and our expression for the transform has to converge for that value of z. All right, x of minus 1 times z. And z is huge, isn't it? It's infinite. So we can't have a non-zero value for a negative time index at 1, minus 1. Same at minus 2. That's z squared. That's even worse. Sorry. Those study buddies, they mess up your eyes and everything else. If you don't know what I'm talking about, I'm sorry. You missed out. What was I trying to do here? Now, for an outer region of convergence, that now implies which time indices are valid. Non-negative, right? Now these can be non-zero. So this is now one-sided and right. And if you wanted to, you could then do what we just did, was to examine x of minus 2, z squared, x of minus 1, z, etc. That implies then that x of n must equal 0 for all n negative, for an outer region of convergence. For an annular, we can have poles on either side of the annular region, of the region of convergence. And that's when it gets a little bit more interesting. For our annular region of convergence, our poles can be in here and they can be out here. But the region of convergence is relative to these poles, meaning these poles are interior to the region of convergence. Those poles are associated with positive time indices. So those modes would be raised to positive values of n. The other poles are exterior to the region of convergence, which was associated with the inner region. And these then, those modes would have negative indices. And that's how we can then play with the annular region of convergence. With the annular region of convergence, modes interior to the region of convergence are n greater than or equal to 0. Modes exterior to the region of convergence are associated with n less than 0. And now that is completely separated from the next concept, which is your time domain response bounded or unbounded? That's disconnected. I mean, it's related, but it's not implied by any of this other information. It's found from this relative relationships, but now you could have a bounded or unbounded response, and that's going to depend on the magnitude or the modulus of the mode in question and let me just say on the modulus of the mode. If we have non-negative time indices, and these are going to happen for exterior and annular regions of convergence. If the mode is such that the radius is less than 1 of that mode, with n greater than or equal to 0, what's that tell you about the response behavior? Is it bounded or unbounded? It's bounded, isn't it? So now we have a bounded response. Well, maybe I did want to say that. On the modulus of mode and time index, let's say window. So with the mode having a modulus or radius inside the unit circle, for positive or non-negative values of n, we get a bounded response. If our region of convergence, let's say, was exterior to 4, we had a pole, let's say, at z equal 4, then we have 4 raised to a positive index. That's going to go crazy, isn't it, with increasing time? So the question was, is this greater than or equal to 1 for R? If R is equal to 1, magnitude-wise, you're right on the unit circle, and what's going to happen? It's just going to oscillate, isn't it? It's just going to sit there and oscillate. It's not going to decrease. It's not going to increase. And that's why I'm not on Dancing with the Stars. Sorry for you at home, you didn't get to see that. Oscillation. But it's on the unit circle, it's just going to sit there and oscillate. That's like in the continuous time being right on the imaginary axis. So if you wanted to build an oscillator, you would locate poles on the unit circle in the discrete time case. So really, it does need to be strictly greater than 1 to be unbounded. So now the one on top is, I like to think of it as less than 1, because what can happen is if you have poles right on the unit circle and you excite them at that natural frequency, you're going to now get a time multiplication on that sinusoidal response, and it will go unbounded. So I like to keep away from the unit circle unless I'm trying to create an oscillator, because I could have a bounded input and an unbounded output with something on the unit circle. So I like to just make the inequality strict, and then it's clean. If somebody says, oh, you've got something on the unit circle, then you tell them, I wouldn't want that unless I'm actually building an oscillator, because somebody can now find the sweet frequency, the correct frequency. They can excite that system right at that natural frequency, and you can have an unbounded response. Okay? And then the other thing that we can, so that was for one possibility, non-negative time indices. We also can look at bounded behavior for negative time index. Well, or maybe I should say negative time indices. Meaning here, if you have a mode with R less than 1, what's that going to do in the time response? You now have 1/2, let's say, raised to a negative power. 1/2 to the -1. That gives you 2. 1/2 to the -2. That gives you 4. You now have that 2 flipped up with positive exponents. It's going to go unbounded, isn't it? This now says, bless you, that you have unbounded response. And if you have R greater than 1, negative time index says you have an inner or annular with poles outside. Now you have a bounded response. So that is the region of convergence. That's what you need to know. The three types, and whether your time domain response is bounded or unbounded. That's not that difficult, I don't think. You just have to kind of pay attention and be careful. Let's now look at inverse C transforms. Y of Z equals something. What's critical here for inverse C transforms? You're interested in the denominator, aren't you? So now you really want to check the denominator, or the roots of the denominator. Let me say check denominator roots. And that's going to influence what you see in your inverse C transform. If you have real roots in your denominator, your poles are real, what kind of a response structure do you have? A decay or an increase, right? It's going to be exponential. It could be a decay, or it could be an exponentially growing. I'm just going to say it's an exponential response structure. It's 1/2 to the n if it was inside the unit circle, and let's say n was non-negative. If it's complex, now you have an exponentially damped sinusoidal response structure, and the damping could be negative damping. It could be going unbounded. It's just easier for me to say exponentially damped instead of exponentially damped or positive exponential, just damped with a negative. Okay? So you could have, if your indices are non-negative, you could have poles in or outside the unit circle, and they're complex. If they're inside, then you have damped sinusoidal response. If they're outside, they're going unbounded with a sinusoidal oscillation. Now, if we looked at some examples of this, suppose y of z is now z over, whoops, and I'm going to not necessarily factor things. I may give you quadratic expressions and hope that you can do the quadratic formula. If I give you now z squared minus 0.75z plus 0.125, and maybe I say the region of convergence is z greater than 1/2, what's going to happen? Well, I hope that you don't try to, oh, it's a quadratic, that means it's complex. No, not necessarily. Factor it first. And this now is just z minus 1/2, whoops, and z minus 1/4. Is that right? So if you multiply that out, you better get what I just wrote down. 1/8 for the product of those two, and their sum gives you 3/4. And this now, you can find how much of each mode is present by looking at the partial fraction expansion of y of z over z. You force that z in the numerator when you're done by putting it underneath y of z to begin with. So that now you have an a1 z minus 1/2, a sub 2 z minus 1/4. And y of n then becomes, with the a's, you can find those, and you now have 4 1/2 to the n minus 4 1/4 to the n greater than or equal to 0. That's because we had a region of convergence that was an outer region of convergence. And it was beyond this largest pole. That largest pole, now is this time response bounded or unbounded? Bounded, and the region of convergence actually contains the unit circle. And that says, oh, then it better be bounded. Now, let's look at the same kind of thing, but now you know what I'm going to do. We have the other case. Suppose somebody gives you y of z equaling z times z minus 3/4 over z squared minus 0.5z plus 0.625. And now we want the region of convergence to be bigger than the square root of 0.625. Well, now if you factor this, you will get complex roots. And the complex roots I like to write in their rectangular form sometimes. And I now know the real part is 1/4 and the imaginary part is 3/4. I now have complex poles at 1/4 plus and minus j 3/4. And if you now think of that, you could say, well, I want, and now in terms of playing with complex roots in the discrete time case, now it's sometimes easier to write those in polar form. Meaning if I now say that z is equal to 1/4 plus j 3/4, I know the magnitude of z. And I just computed that, I hope, before I started. And that's about 0.8, a little bit bigger than 3/4, because we're adding 1/16 to that and then taking the square root. And the angle of z is now 3/4 divided by 1/4, or the inverse tangent of 3. So that's a bigger thing than 45 degrees. That ends up being in radians 1.25, and degrees it's 71.5 6 degrees. So now I know what z is. It's some radius at an angle theta sub d. That being said, let me do just what I did in the real case. Now I have y of z over z. I'm going to say, well, that's just some complex number, partial fraction expansion coefficient, some residue, k1. K1 can be complex. Z minus r e to the j theta sub d. That's the pole at r at a plus theta sub d. That's the factor for that piece. And then I have, actually its conjugate, k1 star, as the partial fraction expansion coefficient for r e to the minus j theta sub d. Now, I can find k1 pretty quickly. K1 is just, it's y of z over z evaluated at the point z equal to r e to the j theta d, or when that denominator vanishes. Meaning k1 is now y of z over z is just z minus 3/4 over the factor associated with the pole in the negative z plane. So k1 is now z minus 3/4 over z minus r e to the minus j theta sub d. I've now multiplied both sides through by the other factor, which was associated with k1, and I'm evaluating at the value of z that causes the k1 denominator to vanish. Is that making sense? I'm just taking y of z over z, multiplying both sides by the factor associated with the k1, and that will isolate k1, and now I evaluate it at that value of z that causes this denominator to vanish. And I can do that number. It's going to give me a complex number, and I can get k1. K1 is now this r, and we just found that, e to the j theta sub d. We know what that is as a complex number. This is now r times, r can factor out, and I have e to the j theta sub d minus e to the minus j theta sub d, and that's just related to a sign, isn't it? So I hope that I've convinced you that k1 is a complex number in general. It has a magnitude and an angle, just by evaluating this expression. This is just 2j sine of theta sub d, the denominator. R is whatever we calculated it to be, a little bit about 0.8. And then we have e to the j theta sub d could be cosine theta sub d plus j sine theta sub d, and you have a complex number for k1. If we now have a complex number for k1, we immediately can write down what y of n is. It's simply 2 times the magnitude of k1, which we just found, if we found k1, r to the n. R was our radius of the poles, the complex poles. We now just scale that by n every time. We have cosine theta sub d to the n. We know what theta sub d was. That was the angle of those poles, plus the angle of k1. And we had an outer region of convergence, so this is valid for non-negative values of n. Now we can go back in time and put on our 2-year-old hat and say, why? Where did that come from? Suppose that we now, well, knowing this expression, we can multiply both sides by z, and now we have y of z as k1 z over z minus a number, plus k1 star over z minus that number. And we know how to inverse transform that for real numbers. Let's just do it for complex numbers. The same structure. Meaning, y of n is the partial fraction expansion coefficient times r e to the j theta sub d to the n plus k1 star r e to the minus j theta sub d to the n. That's just how we inversely transformed z over z minus x, where x now is a complex number. But k1 we said could be a complex number. This is now the magnitude of k1, e to the j angle of k1. I'm just rewriting k1 in a polar form. Magnitude and angle, where the angle is e to the j at the angle. R to the n, I can now split that product of r and e to the j by the exponents, the way the exponents work. E to the j theta sub d times n. The second term, the conjugate of a complex number, is the same modulus. It's the same distance away from the origin, so the magnitude is just k1. Its angle, since it's the conjugate, is the negative of the other angle, the angle of k1. It's now the negative of k1. And we have this other terms, r to the n, e to the minus j, theta sub d n. Now we can combine these angles. K1s are the same, the r to the n's are the same. We can factor all of those out, and we now have k1, r to the n, and we have an e to the j, theta sub d n plus the angle of k1, plus e to the minus j, theta sub d n plus the angle of k1. Just factoring those terms out. But what is this in square brackets? That's 2 times the cosine of the argument, theta sub d n plus the angle of k1. And that's what we said we had for y sub n. That's 2 times the magnitude of k1, r to the n, cosine of theta sub d n plus the angle of k1, n greater than or equal to 0. That's y of n. That's why it was what we said it was. And you don't have to rederive that. You can just write it down. If you know what k1 is as a complex number, now you can just write it down. That clear? That's inversely transformed. Reals, complex. You just have to find their partial fraction expansion coefficients. Just be careful when you do that with your calculator. Sometimes now the calculator will put a 2 in front of your z, for example, in the denominator in your expansion, and it gets a little ornery. But the process is there. Yes? Pardon? So now what's the significance of the region of convergence in that last example? I think is the question, right? So now you have to be told the region of convergence, otherwise you don't know what time indices this is valid for. That all goes back to inner, outer, or annular. In this case, we have an outer region of convergence, that immediately says that our poles are interior to the region of convergence. That means that our ends are non-negative. So that region of convergence, magnitude of z greater than the square root of 0.625, that's outside the poles because that's their radius. That now is what gave rise to that, n greater than or equal to 0. The fact that we said we had an outer region of convergence translates into where that's defined in terms of little n, the time indices. Does that answer your question? So now, is this particular y of z that we started with, does it lead to a bounded little y of n? And now we need to say, well, what was r? R, for those of you in class, was 0.79. It's inside the unit circle, and for non-negative values of n, that's a good thing. That's now going to be 3/4 squared, 3/4 cubed. That's something less than 1 getting squished, and it's just going to collapse. So this will be a bounded, this is an exponentially damped sinusoid. Is that clear? That help? Now, what? Sure. Yes. So now if the region of convergence, if the z was less than, the magnitude of z less than the square root of 0.625, then we have these time indices being negative. Then it's an unbounded sinusoidal response, because we now have something less than 1 raised to negative powers, which will go unbounded. Yes, it will just change the time index. It'll make your ends negative. So we need to know not only the expression for y, but the region of convergence to allow us to tell whether the indices are negative, positive, etc. So we need 2 pieces of information. We need the transform and the region of convergence. Second half of the exam. And hopefully we'll do better than, never mind, Saturday. Discrete equivalence. We really sort of have 2 different pieces. We have the zero order hold type of discrete equivalence, and we have discrete equivalence based on numerical integration and pole zero mapping. So those are really sort of the divisions of discrete equivalence. Do I have a zero order hold or do I have something else? If I have a zero order hold, then, and both of these sort of sides can either be done in the transform domain or in a state space representation. We could do either of these approaches. There's really sort of 3 different strategies, but 2 of those are sort of in the same area or type. Let's look at the zero order holds first. Zero order holds, if we do the transform approach, that means that if we wanted the zero order hold equivalent, g of z is now 1 minus z inverse, the z transform of the original g of s divided by s. We put 1 more pole at the origin and then find the z transform. And like I said, that might be easier to do using the table containing f of s and f of z. If that doesn't feel good to you, don't do it. Yes.
Does that table automatically take into consideration over S?
No, that's a good point. The question was, does the table automatically take into account the over S? No, you have to explicitly put that S in there and then find where you belong in the table. Meaning if you now go, if I can find it, here, you now have to isolate these terms in the leftmost column after you've explicitly put in that extra S in the denominator. Now you might have a 1 over S times S plus A1 times S plus A2 plus S times, or plus A3. You now need to do a partial fraction expansion. Now you'll have maybe a 1 over S term, and that's row 3. Now you're in this table. You might have several row 4s, and you would treat all of those like row 4 individually. Meaning, you, wherever I was, you explicitly put that extra S in the denominator, do the partial fraction expansion, and then try to find those separate pieces in the table. Then the table is applicable. Is that clear? That the table does not automatically account for that extra S. Now, one of the tables I produced in one of the lectures, it did that. I said, oh, we want the zero order hold of K over S plus A. Then we went through the steps of K over S times the quantity S plus A, and we found what the resulting zero order hold equivalent was. But we had to do that in 2 pieces using 2 rows in that table. Does that help answer that question? Yes. So now the question was, do you still need to do the inverse Laplace transform? Not explicitly if you use this table. Meaning, if you now have script z, you're trying to find the inverse z, or you're trying to find the z transform of some Laplace quantity. Let's say it's, well, 8 actually sort of does that for you, doesn't it? 8 sort of sticks an S in there if you wanted to use that directly. Then you would just go over here to this now and find what the Z transform of an A over S times S plus A equals. Now you may have to force that A in there, but you can do that by multiplying by 1, where 1 is whatever it needs to be to give you an A in the numerator. Then once you have this A over S times S plus A, you can immediately slide over here. Now, if I want this capital X of Z in terms of Z, you might have to scale this by Z squared. But that's okay. Z squared divided by Z squared, you can scale it by 1, where 1 is this nice Z squared over Z squared. They have polynomials in Z in the numerator and denominator. Your question? I almost forgot the question. But you don't have to explicitly inverse Laplace transform. You don't have to get this second column, then sample that to get the third column, and then get your Z transform. You can skip those 2 steps now with this table. Yes? It might be nice. So the question was, do we have to give you any information? Sorry, I'm oversimplifying the question. But I don't know if you looked at your neighbor, and I told you in the policy not to do that. So I have eyes in the sky. We'll be looking at you. But now what you can do is you can say row 8 in table. And then if you use, because otherwise I might say, where did that come from? And then I'll say 0. If I can't figure it out. But if you say row 8 and it actually should have been row 12, I'll go, I'll give him a half a point out of 30 instead of 0. So you'll get some partial credit if you tell me what you're doing. I'm being a little facetious, but hopefully, yes, you should tell me. I mean, if you're using table 9, or I'm sorry, row 9, then I know where it's coming from. Okay? Other questions on that? If it's pretty obvious, then you could just write it, but I think if you spend 2 seconds looking at it at the table, I would maybe say row 3. 4. Doesn't take much, and then if there's a mistake, I kind of know where it came from, maybe. That's using the transforms. If you use the state space approach, again, we're still on the zero order hold equivalent. We haven't changed from that. Now we have phi. The system matrix in the discrete time state space representation is e to the a t, where this is now e to the a little t with little t replaced with capital T. You could find, if you needed to, e to the capital A little t by hand, doing it by Laplace. Well, so e to the at is now the inverse Laplace transform of si minus a inverse, and that's by hand. Which means you might have to invert a 12 by 12 matrix symbolically if A is 12 by 12. Just saying. Thought I'd use the terms that people are using these days. Just saying. Now I've dated my lecture. Can't show this in 2055. Source phi. You can still watch it on YouTube. YouTube will be replaced. Gamma, boy, that's a terrible gamma, so let me correct that. Gamma is the input matrix, and that's, you need this e to the at to compute gamma. That's this integral from 0 to the sample period, e to the a, some variable of integration, eta, b d eta. Now you could do that numerically, these phi and gammas. The phi is now I plus at psi, where psi, well, let me give you gamma. Gamma is now psi tb, where psi is now I plus at over 2 times I plus at over 3, I plus at over 4. You're going to sigh in a minute. Okay, so I'll quit. At over 5, and then you just close those up. That's for n equal to 5, capital N equal 5. And n is just a number that you select to try to minimize your numerical accuracy, to make the accuracy good. And for what we've been doing, 4 has been far enough for our 4 significant digit accuracy. That's the zero order hold equivalent. You can do it by hand, the transform way. You can do it with state space by hand, or you could do it state space numerically. You need to know how to do all of those. It may be a little challenging with a 12 by 12 matrix to do psi, but you don't have to square or cube, and that's why this psi is important. You're not raising a to the 12th power. You're sort of stacking it up properly, and that has better numerical properties than trying to do a to the 12th, a to the 13th, etc. If you just use e to the at, that formula directly. Now, if we change to the other side and do numerical integration, discrete equivalence, now we have, with the transform method, we have the forward, we have the backward, and we have the Tustin. Tustin being the bilinear or the trapezoidal. That's the verbiage, I think, in MATLAB. They call it the Tustin. But all of these, they start to look the same. If you they all have similar pieces. The forward, again, this is sort of, S is like differentiating. Well, in discrete time, what do you do to differentiate? You compare a forward and a backward time-indexed quantity and divide by the sample period. So the forward is just z minus 1 over t. The backward is about the same, except now you're looking back, and that means that you really have this z in the denominator. So you have a z minus 1 in the numerator, a t in the denominator, and a z downstairs. For the Tustin, you have a z minus 1t, but now the Tustin is sort of an average of the two above. Z plus 1 over 2, that's sort of the average of the difference, but that 2 can go upstairs. And so you can kind of see how these three are not too far from each other as far as numerical integration approaches. And what do? You plug in that expression for S if you want to use one of those three in the transform approach. And your calculators can do that. If you just say width, you do the vertical line, you write down S, you type in G of S, and is whatever it is, 4S squared plus 2S divided by S cubed plus something. Then you say vertical line with S equal to this mess in Z's, and it'll get it for you. So I may not have you do that because people obviously have a little bit of an unfair advantage if they have a calculator that does symbolic algebra. But you need to know that you can do that. If you do the state space formulations, you better have those on your crib sheet. You don't have to derive these. I don't know that you'll have time to derive it. Maybe you will. But be able to apply those. That basically means calculate a capital phi by some combination of t's and a's and b's and inverses, etc. I think for the forward, phi is I plus capital A times t. That's a quick way to find a phi if you're in a hurry, isn't it? Just scale the A matrix by a t. You need to know how to find t. What's t? How do you find t? If you're not changing the dynamics, so now A is representing your dynamic behavior in what parts of A give you your dynamic behavior? The eigenvalues of A. You compute the eigenvalues of A, you find how big they are, what their natural frequency is. You say, oh, let me sample 30 times that. That's your omega sub S. You find your capital T from that. Now you have capital T. You can find a quick phi. Phi is I plus AT. Boom. There's your system matrix for a discrete time discrete equivalent. Yes? So now if you're taking the eigenvalues, what you would do is hopefully all of those are in the left half plane, and then you would take the largest one, that's the fastest one, right? Now you're looking at eigenvalues in a way that you would say, okay, those are supposed to be conjugate pairs. The fastest one is that one. This is the slow pair, and that's going to dominate your response in the time response, but this is going to be the fastest one. So you base your sampling on the fastest. You find that radial distance to that fastest pole, and you say, that's my omega sub n. Let me sample 30 times that. Now find t from 2 pi over t equal to that omega sub s. Is that clear? So be able to apply those numerical integration, state space techniques. The last thing that we will talk about is pole zero mapping. And what's critical here? Well, I'm assuming you can map z is equal to e to the st for the poles and the zeros, for the finite zeros and the poles. What you're looking for here, the pole zero excess, that's going to lead to so many z plus 1 factors in your numerator. And you match the gains. Now, matching the gains, what can you do? Well, there's really just a few possibilities. Suppose the gain at DC is bounded and the gain at infinity is 0. Where would you match the gains in your transfer functions? At DC, at low frequencies. So this now says match at DC, which means Z what? Is that okay? So that's sort of a low-pass behavior for your starting G of S. If it has a bounded low-frequency gain and its gain goes to 0 at high frequencies. So you plug in S, and if you have a pole zero excess and your transfer function's stable, that means it's well-behaved, then it's going to vanish, isn't it, at high frequencies. It's a low-pass behavior. The Bode plot you can maybe sort of see. The other possibility is you have the gain at DC is 0. The gain at infinity is bounded. Now what do you do? Now you match them at infinity. So that now you are looking at G of S as S goes to infinity. Maybe you have the same order of numerator as you have denominator, and now you're just looking at the leading coefficients in the numerator and denominator, their ratio, to find what this gain will give you. And you set that equal to G of Z at minus 1. If those two fail, then you decide where you match the gains. Okay? That's why they're paying you the big bucks, right? That's why you're going to school. What could happen? Well, if you had a bandpass filter, that's another case. Zero at DC, zero at infinity. Well, find a sweet spot. Find something in the pass band. Now that's equal to some frequency, and map that to, let's say, someplace on the unit circle in your G of Z. Your unit circle is e to the j, whatever that frequency was, times t. To do this stuff. So that you can get the big bucks if you haven't already graduated. Some of you are already enjoying that extra motivation. Questions? Yes. The question on the homework, I think I wanted to give you something to sort of hang your hat on. The question was, why did you mention a bandwidth of 10 hertz? Just so that you can see what that might look like, what G of S is. So a low-pass filter, and what was it, second order? Now you know that it's flat out to 10 hertz, which is 2 pi 10, 20 pi. Oh, now I'm hungry. Why'd you ask that question? So now we have 20 pi's, which is about 60, right? So now we're going out to omega equal to 60, and then we start rolling off 2 poles. We're going down at 40 dB per decade. Know what the Bode plot looks like. It's flat, and then it starts rolling off. And you sort of know where that is, but you're matching gains at low frequencies, at DC. That don't involve pi. Thursday you can do as much pi as you want. But you need to do something before Thursday. You need to ace the exam on Wednesday. Okay? So I'll see you on Wednesday. I do have the normal office hours leading up to that. Good luck, and get your rest and your studies.